thank you and ACS and Dr. Deeksha and our whole team for giving me this opportunity. It's a much needed initiative, especially in the way the things are turning around with COVID. There is going to be a new normal established, and online lectures and certainly online education and discussions are the way forward. I strongly believe that. Today I'm going to talk to you about, like the subtitle says, energy everywhere, and can we store it somewhere? This title itself is kind of an inspiration from the poem or the literature rhyme of Ancient Mariner, where the famous quote goes, water everywhere, not a drop to drink. So the story goes like the person is stranded in the middle of a sea where he has water everywhere around him, but he can't use it for drinking because it's basically salty and not suitable for drinking. So similarly, what I want to impress upon today is the concept that we are surrounded with energy, but the main challenge that the scientific community and the industrial community is facing is that how do you store this, or how do you harness and store this energy somewhere? And that's going to be the central theme of today's presentation or discussion going to be. So let me just go to the next slide. So if you see, just to re-emphasize my point, solar energy, wind energy, all these are huge sources of energy which are available in plenty, and they are all everywhere around us. For example, just the solar energy, incident solar energy on the Earth or in Indian geographical area turns out to be about 10^15 watt-hour per day. And in spite of that, we are suffering, and there is a huge energy demand that is building up. That's because, and similarly, not many of us realize that even when we do a simple act of walking, when we walk around, use our feet, we spend energy to do that. Every step that we take, an average human being of say about 75 to 80 kilograms, every step that he takes exerts energy. He spends energy equivalent to 1 joule in every step. That means if you take 1 step every second, that actually translates to 1 watt of energy which you are spending. So that means there is such a simple act of walking has huge amount of energy stored in somewhere. It's dissipating the energy. Similarly, there is plenty of energy around us everywhere. The challenge is to kind of harness it and store it somewhere. Why do I say that? That's because all these sources of energy, including solar, wind, or when you the energy or the power that you exert when on the ground when you're walking, everything are highly intermittent sources of energy. That means it's never stable. The solar energy, like you can see, is fluctuate every day. It fluctuates every hour. It fluctuates. Similarly, the wind energy also, and if you can see from this graph, it fluctuates rapidly. So it's not a continuous source of energy, but rather intermittent. This is more so felt in the case of when you walk. Every step that you exert goes through the power output goes through a maximum and then dies down just before you take the next step. So this intermittent nature of these energy sources is what is really the challenge in harnessing them and storing them. And that story of how we capture this energy or how to store this energy is what we are going to go through in this in the next 20 to 25 minutes. So if you look at this, what does the future of energy storage look like? So when the electronics was first developed, people were building computers as big as the size of a small hall. This was a photo which is taken from the very first computer which was built. And this whole entire assembly that you see here is a first generation computer. And you had huge vacuum tubes to do the calculations. And it could manage roughly about 2 to 5 calculations per minute. This was about 5-6 decades back, 50 to 60 years back. But when you see that from that point onwards, we have progressed so much in technology that right now your smartphone can do millions of calculations per minute. right in the palm of your hand, you can do millions of calculations per minute. And this is because not only has the size of this devices reduced, the size of technology reduced, which is called miniaturization, it has also become more powerful and more versatile. And that is one of the primary reasons why we have electronics as a ubiquitous entity in society today. Now, if we progress along this, yes, Google has been coming out with this concept called Google Glass. You have Samsung and Fitbit coming out with smartwatches. Now, where do we go next? What is the next big technological leap that is going to happen? If you want to answer this question, what I strongly believe in is that the next big technological leap is going to be devices which are actually integrated into clothing. So now you imagine your shirt or a t-shirt which you're wearing is able to do computations, is able to do calculations, is able to process data for you and give you inputs and outputs. All this requires energy. Now the question is, if at all your shirt can do this, how does where does the energy come from? That's going to be a very, very important question that that both scientists and technologists should combine and try to answer. Now, if you look at that, we get into this area called wearable energy science and technology. This is nothing but 3 simple components, all of which are available on your apparel or your shirt. One, you have a energy harvester or a generator, that which processes all our mechanical actions and converts them into electrical signals. Then you have an active component, which could be a sensor, a device, a process, a central processing unit, anything that can process data in a form that is required by you. It can be a heart monitor, it can be a blood pressure sensor, it can be a diagnostics, anything that would form an active component. But between these two, the harvesting and the active component is the key important factor of energy storage device. And this is something which we are going to look at. Now, if you look at this, it's the area of applications is very widespread. Like I said, it can span healthcare monitoring, online devices, sensors, movement sensors. It also has a huge significance for defense and military, like communication, location transmitters, environment sensors, and so on and so forth. So the list is actually endless and can go span across a wide variety of applications. So what we are essentially talking about is something to power your smart lens, something to power your smart band or your smartwatch. And if you see, the range of power consumption spans all the way from microwatts to watts. That means you have, whenever you try to design devices, energy storage devices for such applications, we need to think of the entire energy power consumption spectrum, which is at least 6 orders of magnitude, ranging from microwatts to almost watt in hour. So that's a very difficult task to do that. So what are the other scientific and technological challenges that that we'll have to face when we do this? We have 2 primary parameters called energy density and power density, which I'll be repeatedly referring to in my talk during the course of my talk. So I think that this is the right point to kind of explain what is energy density and power density. Suppose you take a battery or any kind of energy storage device, the amount of energy, the quantum of energy that can be stored in the device is called the energy density. But the rate at which the energy can be taken out or put in is called the power density. So one is an absolute parameter, the energy density, which talks about the amount of energy which you can store, and the other is how fast can you put it or take out, or put in or take out the energy. That is the power density. So that you can easily visualize it in this form. So suppose you have a jar of water which can hold about 5 liters of water. That 5 liters pertains to the energy density. Okay. Now, depending on the mouth of the bottle, if the bottle is large or small, you can the amount of water which can come out is basically controlled by the diameter of the mouth. If it has a very wide mouth, you can put in or take out a large amount of volume of water instantaneously. Whereas if its neck is very small, if its mouth is very narrow, then you're basically limited by the diameter of the mouth when you try to put in energy or take out energy. So then so that is what energy density and power density looks like. And the other critical parameter when you look at energy storage devices for the kind of applications that we have discussed so far, is everything has to be in solid state. That means even the electrolyte has to be solid state. And there you have a very important challenge or very important roadblock of how do you create a solid-solid interface, because essentially your electrode has to be a solid and also your electrolyte has to be solid. So here you are talking about interfacing and tuning solid-solid interfaces. And plus, these are the scientific challenges. Now, when you want to put it on a t-shirt kind of a platform, it has to be biocompatible, it has to be mechanically robust, long lifetime, washable, even washable. You can't every time take out all these devices and then when you put your clothes for washing. So all these form the technological aspects. But coming back to the scientific aspect, like what Sir Volpe and Pauli quoted, God made the bulk, but the interface was invented by the devil. So essentially, when we are trying to devise a all solid state energy storage system, what we are essentially trying to get to is understanding and playing around with the solid-solid interface. And that means we are actually having a devil as the problem. So now, how do we do this? There are various methods, various champions of this such kind of wearable technologies. But today, for today's discussion, I'll be trying to go through only what we are trying to do in our lab at IIT Bombay. So what we are focusing on are these devices called supercapacitors. Everybody knows what a capacitor is. It's basically two metal sheets which are sandwiching a dielectric or an electrolyte. So you have a metal sheet, two metal sheets in between which you have an electrolyte. And then for such a parallel plate combination, you can write down the capacitance as A epsilon by D. Okay, where epsilon is the dielectric constant and D is the distance between the two plates, and A is the area of each plate, or the interfacial area between the electrode and electrolyte. Now imagine that C and W increases with area. So the capacitance actually increases with area. So what we are essentially going to do is, in an effort to increase the capacitance, we can increase the area. This area being the interfacial area. Now if we don't have two clean metal sheets, but rather roughened metal sheets of which provides more of an interface between the electrode and the electrolyte. So that is what is depicted in this picture. So you have rough corrugations which are basically giving you a more of an interfacial area, and that gets us into the realm of supercapacitors or ultra capacitors. In this case, what happens is basically depending on the potential you apply through the metal electrodes, you have formation of electrical double layer at the interfaces. That is, if you apply a positive, if this is the positive pole, then you have negative ions from the electrolyte crowding at the interface in order to form what is called as electrical double layer. Of course, the structure of the electrical double layer is much more complex than this. Okay, but what I'm trying to give you is a very preliminary understanding of how a supercapacitor works. So now, once this electrical double layer forms, then you can observe it by running what we call as a cyclic voltommogram, where you have current versus voltage. You will get a very symmetric and rectangular shaped CV, and the area subtended by area under this graph is going to give you going to be proportional to the amount of energy that is stored. That means we are talking about the energy density when we calculate the area under this graph. So these are rough terminologies that we have defined before we get into the actual work. So essentially what we need for designing supercapacitors is we need very chemically inert material, because this supercapacitor, the concept of supercapacitor is valid only when you don't have any Faradic reactions happening. That means there should not be any electron transfer across the interface that is happening. It's purely electrostatically driven electrical double layer formation. So it should be electrically conductive as well, with a large surface area. And naturally, you can see that since capacitance scales with area, you are talking about larger surface area. Although over the last 2 decades, this concept of larger surface area has been refined to include the porosity parameter as well into this. So now, for this particular supercapacitor, we wanted to start with a material called carbon nanotubes. These are basically sp2 carbon systems, carbon frameworks, which are arranged in the form of a hollow cylinder. The good thing about this is that it has a huge surface area. It's electrically conductive, and these two and are also chemically inert. So it's very highly chemically inert, because in organic chemistry, chemists would tell you it takes a lot of catalysis or a lot of energy to break open a CC double bond. So it's very chemically inert, electrically conductive, and serve high surface area material. And these are aspects that we are going to use in the device that we discuss. So what do we do with this? This is how we make the carbon nanotubes. So for the way we make them is through a process called chemical vapor deposition. Take a silicon substrate, put a catalyst layer on top of it, plunge it into a furnace at high temperature, and basically flow in the carbon source. Now, the chemistry that happens is that the carbon source under high temperatures, typically the temperatures range between 700 to 800 degrees centigrade, they undergo cleavage. That means they break down, the carbon source breaks down, reacts with the catalyst or dissolves into the catalyst, and reprecipitates as carbon nanotubes. Now, if provided all the conditions are optimized, we get what we call as vertically aligned forest of carbon nanotube. This is just a 1 by 1 centimeter substrate on which you can see vertically aligned black material, which we call as forest of carbon nanotubes. By the way, this height of this structure is about 400 microns, and we can get it in roughly 10 minutes of growth. Now, what do we do with this? The first thing is to see and understand what the material is. So the transmission electron microscopy, as shown here, tells you that the material is completely clean, unique monodispersed carbon nanotubes, single wall carbon nanotubes, and there is absolutely no impurity present in this, which means that it's more than 99.5% pure carbon nanotubes, single wall carbon nanotubes. Also, if you look at the cross section of this forest, you see that all the nanotubes are aligned with respect to each other. Now, just imagine, just to give you a sense of this, how much material we are making in roughly about 10 minutes, I'll spend a minute on this. So you just do a thought experiment. There are about, you see, this is the head of one nanotube, this is the tail of another nanotube. So each nanotube has a head and a tail portion. So you start taking out each nanotube, connect the head to the tail, and thereby make a long fiber. What you would end up with is a fiber that is so long that you can go around the earth with nearly 25 times. That's the length and the mass of material that you can make within about 10 minutes under laboratory conditions. So that's a very powerful material that we're talking about. So now, but being chemists, we are no longer not very interested in working with direct solid state materials. We prefer more the weaker chemistry. So what we do is we take the carbon nanotube powder and then stabilize them in aqueous media using suitable surfactants. And this we call as a ink, carbon nanotube ink. So now the carbon nanotube is very uniformly dispersed in the ink using this sodium deoxycholate, the molecule which you see here, as the surfactant. And that makes it highly stable dispersions. We're able to make very highly stable dispersions. Of course, we can, that's the way we look at it, we can do Raman spectroscopy or Raman scattering to actually look at the nanotubes. You will see that there is a radial breathing mode, which tells you that it's a single wall nanotube. You have the D band, which is a defect centered band, and a G band, which is the graphitic band or the sp2 carbon band, which is and the GD ratio typically tells you the amount of defect, the defect density in the nanotubes. So now, since the radial breathing mode, which is unique for single wall nanotubes, the peak position of that is invariant. We know that the structure of the nanotube is completely preserved during this dispersion process. Also, further, we can do zeta potentials and viscosity measurements just to check on the ability, on the stability of these dispersions. Okay, and so next, having got the zinc, there is a lot of possibilities which open up because of the zinc. One of the main distinct possibilities that we utilize is that ink can be coated onto any surface. So now, in this case, we take a simple piece of cotton thread or a cotton ball and then dip coat it through the CNT ink. what happens is that the carbon nanotubes from the dispersion are uniformly coated on top of the CNT, on top of the cotton thread, and the result is what you would get, like a thin piece of thread. Now, how do you know that these are coated? You can either look at the SEM, which shows you a lot of interconnected network of carbon nanotubes. You can measure the surface area, which turns out to be about 900 meters square per gram, or you can also measure the electrical conductivity, which, when the carbon nanotubes are uniformly coated, you would get a very nice ohmic conductivity on top of it. So this process in itself is very scalable and also very easy to perform under laboratory conditions. So now we further characterize this carbon nanotube thread. This is basically the SEM of the thread, which contains carbon nanotubes which are coated on top of it. And you can see that the resistivity does not change whether you hold it straight or you bend it or coil it. That means the nanotubes adjust the mechanical stability of the nanotubes and allows or enables that the electrical conductivity path is maintained completely when you bend it or twist it or roll it. And this is very important when it comes to applications of for wearable electronics. And similarly, you can see that there is, when you do the photoelectron spectroscopy, there is an increase in the electron work function, which tells you that the conductivity is mainly through a hole-mediated conductivity. Now you have this nice thread that you can work with. What do you do? This basically, because it's electrically conductive and it is high surface area, it forms the electrode material of our supercapacitor. How do we interface this with a solid state electrolyte? Because that's the second part of the device. You have two electrodes and you have to get the solid state electrolyte. Now for doing that, what we did was we took a methyl cellulose, which is a polymer, and the biodegradable polymer, and we took ionic liquid and blended these two together, so such that the ionic liquid kind of mixes and blends into the polymeric matrix, and this is how the sheet would look like. So you have a very nice freestanding film which now contains the ionic liquid, and also the mechanical robustness of the film is provided by the methyl cellulose. Now this we call as the ion gel electrolyte. Now you have an electrolyte, you have an electrode. How do you merge these two together? This is we did this through a very interesting process. Basically, we take it to a tailor and ask him to sew one on top of the other. So the way we do that is, you have the CNT, you start weaving threads across this ion gel electrolyte, and you do that in such a way that you have perpendicular junctions created. So what I'm holding is a 3-dimensional 3D printed model of this. So if you see, this is one CNT thread, and then right on top of if I invert it, you can see another CNT thread. So essentially, if I hold it like this, you would be able to visualize that this particular junction, where the two CNT threads, one running on top and the other running in the bottom, where they meet, essentially would start behaving like a capacitor, because you have now two metal surfaces, which are encompassing a solid state electrolyte within which ionic liquid is held. So this becomes a typical supercapacitor junction for us. Now the way to know that this would act like a junction is that you measure the cyclic voltammograms, and you see a very rectangular and symmetric nature, from which you can calculate, which is directly proportional to the electric energy density. So essentially, we have what I'm trying to impress upon you is that we have created micro junctions of supercapacitors which can store energy, and at the same time does not require any lithographic protocols for fabricating it. And this is how a typical device would look like. So then the next part of this is, now that you have made the device, you no longer can, it's not very optimal to expose it to the environmental conditions. In order to protect it from environment, we developed a very simple strategy, which is basically a hot press lamination approach. This approach is essentially what you would do for your certificates or ID cards. You take it through a lamination machine and it gets packed or packaged. We used exactly the same approach, and you can see that the package device here, which is bound by the PET, package within the PET sheets by the lamination approach. So this way we can protect the device from all external environmental conditions and ensure its stable performance. How do the way the stable performance is measured can also be measured through what we call as galvanostatic charge discharge cycles. Basically, there is a charging process where we put in energy into the system, and there is a discharging process where the system or the junction gives back energy to us. And by following this, we can work out the efficiency of operation of the device. And so we see that we have got a very negligible IR drop. That means we are able to retrieve almost all the energy that we put in into the system can be retrieved back. And we can also look at the electrochemical impedance spectroscopy. Rather than focus on DC measurements, we can also do AC measurements, which is impedance measurements, to understand the nature of the interface. And here, as you can see, at a certain fraction of the ionic liquid and methyl cellulose, you see a very low resistance and also a very low charge transfer resistance between the interface that is happening. And it's a single, the semicircle essentially points out that there is a single RC constant or a single process of charging and discharging that happens. And so then once we establish that it's a very nice capacitor device, the junction is a very nice capacitive device that we work with, we can extend the application and do what we call as integrate multiple set junctions, because now all you are doing is just sewing one thread over the other through the electrolyte sheet. So you can have multiple junctions of these devices either in series or in parallel. When you do connect these junctions in series, what you would get is you can access higher voltages. Operating voltages can be much higher than what is possible with a single device. On the other hand, if you don't want a higher voltage but you want a higher capacitance, then you can connect them in parallel, and for the same voltage, when you increase the number of devices in parallel, you can actually start putting in more and more energy. That means you can increase your energy density from the device. So then this is not the only thing that's possible. We can do horizontal tunability, have several such junctions in a horizontal sheet. We can do vertical tunability, all of this which has been demonstrated by us. And essentially, even when you bend the device, you can absolutely have very stable performance. This schematic basically shows that you have 4 devices, each of which is connected by the CNT thread, and so you can bend it into 3, fold it, or even bend it all into a very compact volume, but still the performance of the device is exactly the same. So this essentially tells you that it's a very robust device. And not only that, because we have this ability to connect it in series and in parallel, you can actually also operate the device at higher voltages. And this, you can bend it, the capacitance does not, the shape of the cyclic voltammogram absolutely does not change when you bend it to different degrees. And you can also light, here what we have shown is, we have demonstrated a lighting of a small LED with the energy that is stored in a few junctions of the device. So just a few 3 to 5 junctions of this device, the 3 to 5 junctions that I talked about, supercapacitor junctions, can hold enough energy to power an LED. So now, can I have about 5-10 minutes more? Yeah, Ajay?
Sure.
Okay.
Yeah, please.
So but having said this, we wanted to further probe what the interface really looks like, because that has been the main key question before the scientific community. So we did experiments with electrolytes of various contents, ionic liquid contents, 40 to 60, ranging from 40 to 60 to 80 to 20, and see that there is an optimum level of ionic liquid and polymer concentration, methyl cellulose concentrations or ratios that we have to achieve in order to get the best performance out from the device. As you can see, the 40-60 ratio gives you the highest specific capacitance, the lowest IR drop, and the highest DC conductivity. So this, we wanted to further probe what this 40-60, what is so special about this 40-60 content. For that, we use what we call as a spectroscopic mapping using Raman vibration bonds. So because essentially the polymer and the ionic liquid are both carbon systems, it's very difficult to distinguish between them unless you use a spectroscopic technique. And we use Raman vibration mapping, vibration modes, which are particular to the ionic liquid and particular to the polymer, and therefore we can get a very nice distribution of ionic liquid, or a nice physical distribution of ionic liquid and polymer components. And like you see here, the 60% ionic liquid, which gave us the best results, are ones where the ionic liquid given by the red and the polymer, which is given by the blue trace, are exactly complementary to each other. That means the polymer basically forms channels or pathways within which the ionic liquid is trapped, and this gives you the exact complementary structure. Any other ratio of these two constituents would give you a very randomized structure, meaning that the integrity of the device or the integrity of the electrolyte is lost. Therefore, this Raman mapping has, we think, is a very powerful tool to understand the microstructure and for the first time kind of visualize, spectroscopically visualize the ion transport microchannels into the device. And this is how a 3D image would look like. There are these red channels which pertain to the ionic liquid, the conductive components, and the blue phases, which are the polymer, which is important to hold the physical integrity of the electrolyte, because remember, we are working with solid electrolytes. And further, the last thing which we wanted to do is test the mechanical durability. It's absolutely robust performance over 5,000 cycles. Like I showed you, it's bendable. Not only that, you can actually integrate it onto your clothing. Like what I'm showing you here on the slide and as well as through the video is actually a piece of device which is integrated onto a t-shirt. So you can bend it, you can twist it, you can do whatever you want, just like how you would handle a regular t-shirt, and without any failure of the device. Here you can see that you can actually hit it with a hammer, and even then the device continues to work. You can put it in a washing machine. It can stand more than 10 cycles of washing in a regular commercial available washing machine. And so coming to the final performance of the device or benchmarking the device, you see that the energy density and the power, we talked about two parameters at the start, that is the energy density and power density. See, compared to all other literature reports, this work or the idea or the devices which are made by simple interweaving of electrodes through the electrolyte is able to achieve much higher energy density and power density compared to the previous energy reports. And here I'm just going to show you if it runs. I'll probably show you a piece of, okay, that doesn't seem to run. So the last part which I'll just briefly go through. So now the energy density and power density of the device is far more than what previous reports for certain wearable applications that we discussed show. So that means we are outperforming the device, but we wanted to really push the boundaries even further. One of the things that we were looking for is that so when we wanted to push these boundaries further, one of the questions that we asked is, can we remove the insulating matrix? Because the thread, the cellulose thread, is basically going to give you only the physical matrix on which the carbon nanotubes are immobilized on. So can we, that is not playing any other functional part of it. So can we now do away with the complete cellulose thread and instead have only the functional components? For that, we kind of reinvented the entire device design, and instead of making carbon nanotubes as powder, we started weaving the carbon nanotubes into a form of a thread or a fiber. So now you can see that you can collect spools of this carbon nanotube thread, which are much higher conductivity, much higher conductivity, because this is now pure CNTs without any insulating material. So there is absolutely no cellulose in this, completely made up of CNTs. Therefore, the conductivity of this is about 1000 Siemens per centimeter, at least an order of magnitude what we compare higher than what we got with the case of CNT thread. And the other interesting thing is, because we are winding it, just like how you can imagine like a sugar candy is spun from a container. So the same way we are winding it and forming a form of drawing it into form of fibers, you can see that all the carbon nanotubes are aligned, and this is further confirmed through Raman polarized Raman spectroscopy, polarized Raman measurements as well. That the G band has a peak in the intensity, shows a peak in the intensity at a certain angle, meaning that that particular polarized incident excitation is parallel to the tangential G mode vibration, and so that means the nanotubes are all aligned, preferentially aligned in a particular direction. Now, with this, we wanted to kind of work out a different geometry. So what we did was we started with this coaxial, the CNT yarn in this case, what we refer to as CNT yarn or the CNT electrodes, which are pure CNT fibers made into form of a yarn or a fiber. So we start with this, and then we put the electrolyte. In this case, the electrolyte is polyvinyl alcohol sulfuric acid mixture, and we coat it in a coaxial geometry. And then now this forms a kind of a Russian doll-like geometry. So there is an inner thread, the yarn, the CNT yarn is now covered with the polymer, and then the outer surface is covered with one more layer of CNTs. This CNT is coming from the earlier dispersions that we talked about. So then if you look at the cross-section area, this is how it would look. You have the inner CNT, you have the electrolyte, and then you have a thin layer of outer CNTs. Now, this can also be an exactly same model as a capacitor, or because it's made up of nanomaterials with high surface area, it is a supercapacitor. So then when we operate this device, we were in for even more surprises. One of the things that we didn't discuss about when it comes to energy storage is the rate operability. How fast can you put in or take out energy? Okay, that is exactly the power density. Now, if you see that the black curve, which is basically the device, which is operating at 25 volts per second, which is a scan rate of under a scan rate of 25 volts per second. Now you can keep on increasing it, but then at beyond a certain point, you would see that this rectangular nature falls off. But when you do a simple step of annealing, this annealing which I didn't stress about in the previous slide, this simple step of annealing, you can operate this device at far higher scan rates. You can go even up to 200 volts per second without actually distorting the symmetric rectangular nature of the cyclic voltammograms. That means it is a solid state device which can operate at nearly 250 volts per second. And this is something which is unprecedented for solid state devices. Say for the same device which is not annealed, you can see that at 200 volts, the line becomes a ohmic line, which means it starts behaving like a resistor. Whereas, and there is complete collapse of the double layer, electrical double layer. Whereas for the device which is slightly annealed at 80 degrees, you see that it can go up to 250 volts per second and yet retain its capacitive nature. And remember, all this is achieved in solid state devices. The linearity of response, which is the true feature of a ultra fast, ultra high scan rate capable device, turns out that the device without annealing does poorer than the device after annealing. After annealing, you can basically see that the linearity extends almost to 200 volts per second, which is by far the highest in terms of solid state performance. There are of course being reports or reports which have achieved similar performance, but these are with liquid electrolytes. So essentially, we are working at a frequency response which, even though we utilize solid electrolytes, we are able to match up to the performance of liquid electrolytes. And that's an important feature because we do this by thermal annealing of the interface. And this annealing step that I kept on referring to is basically nothing but heating the device at 80 degrees centigrade for about 5 minutes. What it does really, I'll for the sake of time, I'll kind of skip through this, but essentially point to the fact that we can analyze the frequency response of the device, and turns out that the relaxation time constant is something like 12.7 milliseconds. So essentially it tells you that you can not only put in, you can also take out energy at every 12.7 millisecond interval. So that basically translates, and this is, remember, without using any other current collector. It's basically all carbon material. So this means that you can put in energy and take it out at a very high power density. So this is the second parameter that I was talking about. To really understand what exactly happens at this 80 degrees centigrade, we did Raman profiling of the interface. So this here in this slide, in this photo which I'm showing you, you see that this is the carbon nanotubes and this is the interface, the electrolyte part. Now and these two, if you see here, are nicely separated out before the annealing. There is a CNT domain and an electrolyte domain. Now, when you do this thermal annealing at 80 degrees centigrade, you see that the clear demarcation you observed earlier is no longer present. It basically has diffusionally broadened into each other's domains. That means there is no distinct layer of separation. These two electrode-electrolyte interface has really gelled and created, in that process, created more of an interface which is observed, which is what is established through this Raman mapping. I'm afraid I'll not be able to continue into more discussions. But to summarize this story, what we have done is we've taken a coaxial electrolyte coating. Through this process of simple one-step process of annealing, what we did was we achieved not only infiltration of the electrolyte into the electrode, but also induced chemical functionalities, which if you refer to the paper, you would be able to read it in further detail. We show that the oxygen enrichment and the interface is critical to achieve this ultra-fast frequency response. And that and similar, just like what we did with the previous device, we have also integrated it onto gloves. You can see that absolutely flexible. There is no problem. Even if you bend your fingers and this thin line is the actual device, you would be able to, the performance is not changing. It is just much better than what micro supercapacitors or other fiber-based supercapacitors are able to do. And not only that, it can last for a much longer time. As you can see, it's about 4,500 cycles. Very little degradation of the devices happen. So to conclude the story, what I want to kind of emphasize is that what we have tried to demonstrate to you in this 35-40 minutes is that the form factor, not only is the device material and the chemistry important, it is also important to come up to out-of-box thinking and utilize form factor, bring in new form factors and design factors to enable high-performing devices. That is something which I have done, and also we have engineered the solid-solid interface to achieve seamless ion transport. And not only that, we have studied that through Raman spectroscopic mapping and tuning of the ion transport channels. That the Raman spectroscopy essentially enables us to tune and not only understand but also tune these ion transport channels. And so with that, I would like to acknowledge my group. Mihir and Ranadev were the ones who really did the work I presented today. Enormous support from DST is directly acknowledged, and IIT Bombay as well. And finally, thank you ACS for giving me